This is problem 3 on practice exam 2 of chapter 1 in the book Problem Solving with Differential and Integral Calculus. Problem 3 involves a 1 kilometer time trial, an Olympic track event. Cyclists start from rest, go 4 laps around a 250-meter velodrome for a distance of 1 kilometer. The normal equation that relates the average speed of the cyclist over the whole race to the time to complete the race is distance traveled over time, which is 1,000 meters, the distance of the race divided by t. The normal equation relates the average speed over the whole race to the time to complete the race. World-class cyclists can do it in about a minute, which is right here. Get the difference equation that relates a change in the time to finish the race, delta t, to a change in the average speed. Combine the fractions by getting a common denominator. So let's really think about what we're trying to do here. If we go, say, 3 seconds faster, how much does our average speed over the race change? We want to get a relationship between the change in the average speed over the whole race and the change in the time to complete the race. So let's consider 2 points on the line. Up here, there's one, there's another. These have differences. We want to get a relationship between the vertical distance, vertical change, which is delta V average, and the horizontal change, which is delta T. So if my time changes by this much, how does my average speed change? That's what the difference equation is. The normal equation is this. For time t, it's 1,000 meters over t. And if your time is different, V average is 1,000 meters over t plus delta t. All right, we want to get the change in the average speed, so we subtract these two. That's the difference in the average speeds. So 1,000 meters over t plus delta t minus 1,000 meters over t. This is the average speed when you complete the race in t plus delta t. This is the average speed when you complete the race in t. And if you subtract them, you get the difference. We need a common denominator. And we get one, multiply this fraction, top and the bottom by t, multiply this fraction, top and the bottom by t plus delta t. And now we can subtract the numerators. And we get 1,000 meters delta t over t times the quantity t plus delta t, and it's negative. It should be negative because when your t goes down, this t, delta t is negative. Negative times a negative is a positive. Your V average is positive, right? If you go faster, time goes down, your average speed goes up. Should make sense. On to part B. We're going to draw a tangent line at 100 seconds and calculate its slope, and then estimate the change in the average speed needed to drop a second from your time from 100 to 99. So first let's locate the point right here. Then we got to draw a good tangent line. There it is. Now we have to get the slope of the tangent line. It looks like it starts about 15, goes down to 8, so that's minus 7. It drops by 7 meters per second. And the span is the whole x range, which is 120 to 50, so that's 70. Range is 70. So the rise is minus 7 meters per second. It drops from 15 to 8. The run is 50 to 70. That's 70 seconds. So the slope is minus 1/10 of a meter per second every second. That's the relationship between delta V average and delta T. Now we can use this equation to get the time needed to drop a second, because we know what delta T is. Delta T is minus 1 second. And here's the slope. Now we can estimate V average from this. We know it's not going to be exact because we're wandering away from this point and we're only using the tangent line. But from 100 to 99, the tangent line follows pretty closely. So we can solve this equation for delta V average, and we get plus 1/10 of a meter per second. And it should be positive. Ready for part C. Use the normal equation to calculate the average speed at 100 seconds and 99 seconds and then subtract them. So we're going to use the normal equation to get the difference. And this is the exact difference because the normal equation is given us the exact average speeds. If it takes you 100 seconds to go 1,000 meters, your average speed is 10 meters per second. If it takes you 99 seconds, your average speed is 10.10101010, etc. So the difference exactly is 0.10101, and our estimate from the tangent line was 0.1. So a little bit different, as expected. Now we're going to part D. Use the difference equation to get the answer, to find out what delta V is when you go from 100 seconds to finish the race to 99 seconds. So there's our difference equation, and this should be exact. So we're going to plug in 100 for T and -1 for delta T. So there's the equation. It's going to be positive because there's a negative here and a negative here. And we get what we expected, exactly the same when we subtracted the two normal equations. Minus 0.10101. Same result we got in part C. Now we're going to tackle part E. Use the difference equation we derived in part A to calculate the difference in the average speeds between a trial that takes 100 seconds and a trial that takes 99 seconds. So here, we're not going to use the normal equation twice and subtract the results. We're going to use the difference equation directly. There's the difference equation that we derived. And we're going to plug in 100 seconds for T and -1 second for delta T. We're not going to use the 99 seconds in this equation. Substituting in these values, we get this. There's a negative here, there's a negative here. It's going to make it positive. Doing the math, we get 0.1010101, etc., meters per second. This is exactly the result we got when we used the normal equation twice and subtracted the results. So now we're ready for part E. Part E asks for the linear part of the difference equation. The linear part of delta V average. That should give us the tangent line. Then, for extra credit, we're going to get the nonlinear contribution. So before we do that, let's review this whole problem. We have a normal equation that relates the average speed over the whole race to the time to complete the race. That's the normal equation. There it is. Then we derive the difference equation that relates a change in the time to finish the race to a change in the average speed over the race. And here it is. We checked this by using the normal equation twice. We know it's right. When we did it, we got 0.10101 for delta V average both times. All right, now we're ready to extract the linear part. It should give us the equation of the tangent line. So here's the difference equation. What's the linear part? And it's pretty straightforward if you've done this a gazillion times. And then in the denominator, we have a t squared plus t delta t. We're trying to get the linear part. The linear part is the dominant part when delta t is small, because we want the equation of the tangent line. So delta t, the run here, is very small because we're effectively looking at a point. So if we add a small amount to t squared, it's not going to change it. So we're going to get the linear part where we say, look, we can ignore the t delta t relative to t squared. And we get that. V average, the linear part of delta V average, is minus 1,000 meters over t squared delta t. And it's important, if you're going to understand calculus, to figure out what the heck does this mean. It relates the change in the time to finish the race and the change in the average speed along the line. If you wander far away from here, there's going to be a nonlinear part. This is only the linear part. This is an estimate. It should be really close when delta t is small. So if we pick a point on the curve, the linear part of the difference equation, that part right there, gives us the change in V average along the tangent line, along this line. That's the linear part. This is an approximation because the actual line is curved, but the closer we get to the point, the smaller the delta t, the smaller we go away from the point, the better the approximation. With a t of 100 seconds and a delta t of -1 second, the linear approximation, this is an approximation now. Here's our linear part. It's 0.1. It's close. It's very close. The actual answer is 0.101. 0101. Okay, that's the exact answer. Here's our linear approximation along the line. We start at 100 and we wander over 1 second. This is the result along the tangent line. That's the exact result. So let's try to find the nonlinear contribution. And we have the exact change and we have the linear contribution. So the difference is the nonlinear contribution. The exact change in V average, there's the linear part, there's the nonlinear part. We have both of these. So we can calculate this one, the nonlinear part, by some algebra. And we leave that as an exercise to you. You can pause it and try to get it. So here it is. T delta t squared, it's nonlinear, it's delta t squared. And then the denominator is t to the fourth plus t cubed delta t. And let's check this. We're going to use the nonlinear part and the linear part. The exact answer we know, 0.1, 01, 01, 01, 01, 01. The linear contribution is 0.1. So the nonlinear should be 0.00010101. And we can plug it in to our equation, and that's exactly what we get. So the nonlinear plus the linear is the exact. Now let's check it. Let's wander far away from that point. So we're at 100. We're going to go way down to 70. So our delta t is minus 30 seconds. We cut 30 seconds off our time. So here is the linear part plus 3 meters per second. And we can see we were at 10, we went up to about 13. That's the linear part, the part along the line. The nonlinear part, there's our equation, and we can substitute all the numbers in. Our delta t is minus 30, our t is 100, and we get 1.286. All right. Delta V average, the change, is linear plus the nonlinear, which is 4.128. So our average speed went up by 4.128 meters per second. So here's delta V average, the whole thing. Here is delta V average linear part along the line, that's 3 meters per second. Here is delta V average nonlinear, that's 1.286 meters per second, and the total delta V average is 4.128. And we can check this with the normal equation. If it takes 100 seconds to finish the race, your average speed is 10 meters per second. We've seen that before. There's 10 right there. And if we plug in 70 seconds for t, we get 14.128 meters per second. And the delta V of 4.128 is consistent with that result. So we can see that the linear part is not that accurate because we went too far away. But if we put in the nonlinear part, we get the exact answer. That's problem 3.